me start by saying I'm going to try to go slowly so that you can get an idea of some fundamental methods that we've developed. And secondly, I'd like to start by just looking around and seeing a bit of the background that you actually all have. So, how many of you do fracture? There you go. That was expected. How many of you know about contact mechanics? That was also expected. So one thing that is actually very good today is that you've actually already gone through some of the concept of the approach to the asymptotics that I'm going to show you today with Sylvie yesterday. So I'm not going to be telling you a lot of new stuff, at least at the beginning, and then it's going to become a bit more complicated. So, as the title says, I'm going to talk about development and application of asymptotic methods to fracture and contact mechanics. This is the work I've done during my PhD and after my PhD. I did my PhD in Oxford. I'll show you some background slides, and then I moved to Imperial. But I'm Italian, so if you want to ask questions in Italian later, you could also do that. I can speak French if you like. What's the distribution of nationalities around? Italians. There you go. Very good. Europe. Without Italians. Elsewhere. All right. That's good. Pretty good distribution. Right. Okay. So without further ado, I'll start. One thing. I do tend to speak very fast. So at some point, if I really take the tangent and I go very, very fast, some of you should just stop me and ask to repeat, please. The other thing is, I don't mind being interrupted anytime, any slide. Someone can actually ask questions, okay? So let's start. I'm going to give you a bit of a background. Where is Imperial? Most of you should know, I hope. So Imperial is in the center of London. Pretty expensive place to live, but very nice. It's over 100 years old. We've got plenty of students. We focus a lot on research. So 23% of our students are postgraduate students, PhDs, master students. We obviously have students from all over the world, research staff and professors are also all over the world. They come from everywhere. We seem to be ranked anywhere between the 1st and the 15th university in the world, depending on the ranking you see. This is the front door, very fancy landscape designed by a very good architect. My office is that room over there. There you go. So this is the main road that goes to South Kensington. Here is my room. That's my office. That's the one of the symbols of Imperial is the Queen's Tower in the center of Imperial. How many of you have been to London and to Imperial College? Anybody? None of you? Oh, well, very good. Okay, so if you go to London, because it's very close to the museums, have a walk around. We are very close to the Science Museum and the Natural History Museums in London. So that's where I come from. And if you look from the top, obviously you know where London is. This is Great Britain. We're just down there in the southeast. So that's the campus. As I said, the tower is in the middle. Mechanical engineering is here. My office is somewhere there again. And here is the landscape. So this is Hyde Park in London. This is the Serpentine. This is the Royal Albert Hall, where there is theater and other things. And the museums are here. So here is the Science Museum, and everything else is there. So if you come to London, don't forget to come and have a peek through Imperial. Now, my group, I'm head of this group. The group is tribology. Tribology is the science that studies contact, lubrication, and friction. So it's a fairly big group. We've got 7 academic staff and about 40 students. In total, we're about 60 people. And we study all sorts of things. Anything that has got surfaces in contact is what we do. So we have a lot of tribological application from car engines, aeronautical applications, biological application. In fact, very recently we started a biotribology group within the group, and we do a lot of application on nanoscopic contacts. That's not the topic of today, but we do quite a lot. So if you're interested in other things we do, come and ask me later. And it's a pretty happy bunch of people. And I think if you ever, again, if any of you is interested in a specific application and you come to London, you're free to come and visit me if you like. Now, this work was done when I was in Oxford, as I said. So it all started in a room which is located just somewhere there. There you go. Here is the Keble Triangle in Oxford. This is the center of Oxford. My department of engineering science is there. And my PhD supervisor was Professor David Hills. He's down there. And he was, and he is, the director of the University Technology Center in Solid Mechanics that is funded by Rolls-Royce. And the reason why I'm saying that is because some of the things I'll show you later are directly related to that. And obviously, I didn't move very far after my PhD. I just went from Oxford to London. It's about 60 miles, 1 hour drive, so I was very lucky. But the collaboration with David has been something that actually, as I said, started 15 years ago and is still ongoing. We keep developing techniques that are used throughout the years. So, here is where we are. I told you who I am, where I come from. I told you about my collaborator. That's why I got 2 logos there, because most of this work was done in collaboration with them. Now, let's start talking about the class of today. So I'm going to give you a bit of a background. I'm going to tell you why asymptotic methods are good, in my opinion, and what you can do with them. So before we do that, we're going to go through the mathematical background. Then I'm going to show you how to apply those methods to fracture and fatigue. So I'm going to give you some fundamentals of the methodology, and then I'm going to give you an idea why you apply these methods to notch and crack materials. And then I'm going to take you to how you take these same methods and you start looking at the potential application of these methods to contact mechanics. And in order to do that, I need to first introduce some different classes of contact problems. And then I'm going to show you how to do asymptotic methods applied to some of these contact problems. And in the end, I'm going to talk about how you actually can define failures and try to predict failures in contact using these methods. Okay? So it's fairly streamlined. We can stop anytime. You can ask me questions anytime. At some point, I think during the lecture, I will stop because 3 hours of this is too much. And we can take questions. We can go for some drinks, and then we come back. So let's start with the motivation and the background of the methodology. So in terms of motivation, I'm going to first start with a broad motivation on what I do in general, and then I'm going to focus on the motivation of the asymptotics methods. So very broad terms. My motivations come from the fact that wherever I look around, I have components, I have elements in machines that require study and understanding of contact mechanics, understanding of why, if 2 bodies are touching each other, there is some potential failure damage that comes about by the contact of these 2 systems. So typical example, things that everybody has worked on for now more than 100 years in contact mechanics is transport. Every single part of a car, train, airplane, helicopter has got a lot of moving parts which are in contact. So the engine, the wheels, the bearings in a car, the rotating system in a jet engine, the wheels and the railways, but as well as many other parts in a train, the helicopter blades and the rotors and the motors in the helicopter. So all of these parts have got contacting bodies, and all of these can fail because there is something moving in the system. Now, obviously, things during the years have also evolved. Now there is a lot of focus on energy, so again you've got quite a lot of problems that we're dealing with that are quantum mechanics related. So if you think about your big wind turbines there is a blade running, there is a gearbox behind it, there is a generator. All these parts have got elements in contact. Some of these things have bearings with balls as big as this. So you can imagine that the contact problems with those elements are very different from contact problems where your contacts are very tiny. Here is, for example, another type of project I do, drilling to get oil down from rocks. Here is the tip of a drilling system. So these rotates and excavates down the ground, down kilometers and miles. So you can imagine that you don't want these tips, which are made of polycrystalline diamond, to fail as you try to excavate, because you need to retract this by a few kilometers. You waste a day of operation, and that turns around to be a few million for the company. And I can give you tons of examples. New transmission system for electric cars. They got all sorts of different problems with respect to traditional transmission systems. And then, if you look at this, again, there is a lot to do with the human body. So I'm walking, and I do walk a lot, and I do walk very fast as well. And you realize that any contact in your body is a fatigue problem. So you're actually going to go and run on your knees and walk on your knees for 30 years. That is a few millions of cycles. And obviously, if there is something that causes damage in any of your tissues, that will propagate at some point. And actually, in a simplistic way, lots of your joints in your body are as prone to fatigue as many of the joints you've seen in the cars before. So bio applications are as important as traditional and more conventional applications. And in the years, because there has been quite a lot of development in the nanoscience, you can also imagine that anything that is microelectronics, MEMS and NEMS of the kind, relies on you having switches that this time are nanoscopic or macroscopic usually. And therefore you need to understand how these things work and try to optimize their functioning. So I really usually put this slide up to say, whatever you turn around, there is something that is in contact. That's my specific idea of doing research. I want to understand how, in general, I can solve these issues. So that's where I started my career. I did my PhD in Oxford, and here is the problem I was studying. That is a blade coming off a disc in a Rolls-Royce engine. That's what happens at low speed. That's what happens at high speed. Right, so this is a successful test. You look at this and you think, successful. Not really. It is indeed a successful test. So this is a test that any engine company needs to run to make sure you can certify to fly. Why? Because if you go back to the origin of that slide, this is something that can happen. There is an interface between the blade and the disc in which it's mounted, and if something goes wrong, that blade is released, and you don't want that blade to be released during the flight. I mean, it rarely happens. But if it is released during the flight or during takeoff and landing, which are the most dangerous part of the flight, you want that blade to be contained within the casing. And that's where our impact engineers do a great job, because in that case, they show that yes, if the blade is released, is encased within the engine, it doesn't fly through and kills people in the fuselage, and therefore this thing can be certified to fly, because even if it failed safely. So I did that because my PhD was about trying to avoid that the blades come off the disc, because that's a contact problem. There is a blade stuck in the disc, and it might or might not move as you fly, and therefore after a while you might get some damage. So I started that. as my PhD. I'll tell you more about that later. But I'm also working on all sorts of other conventional tribological problems. So you have gears, bearings, very large transmission systems, and that is one of the things I do. The other thing I do is, because I'm dealing with surfaces, a lot of the improvements on surfaces can be done these days through changing the friction properties. So I do a lot of work on understanding how lubricants can be applied to surfaces. I do a lot of work on coatings and how coatings and smart coatings can improve performances of systems. And I do a lot of work on texturing surfaces, because by changing the surface properties of some materials, you can change the performances. Am I going slow enough? Yes? Good. Okay, so, and then as I said, I also do quite a lot of work on biological systems, or design of new implants that go into the human body, understanding how real things work. We even do work on brains, just because we like doing things different. And a lot of work on very small scales. As I said before, when you go down to the small scales, conventional continuum mechanics really doesn't apply 100%. And so I do a lot of work on molecular dynamics, trying to understand atoms and how atoms interact in surfaces, which is not the topic of today. But again, if you're interested, come and ask. Now, the real motivation of this talk is back to my PhD. Working on those engines, as I've just shown you before, trying to understand some of the issues that you might have if you have stress concentration, if you have actually elements in which you've got either contact or sharp features that result in large stresses. So for example, one of them I showed you already is the fan blade attached to the disc. Another one is when you have two shafts. So this system is composed by different shafts. There is the fan shaft, there is the compressor shaft, and there is the turbine shaft. They all go one into each other. And these shafts are usually linked with the spline. So you basically have a male and a female, and one goes into the other, and they just rotate with respect to each other. And because they rotate with respect to each other, again, you've got contact between the teeth of one and the other. And at some point, you might get a crack, you might get a failure. So what I was interested in, and what most of the group in Oxford was interested when I joined, was trying to understand fatigue failure that come from a system where you've got some contact, being that the spline shaft, being that the fan blade in contact with the disc. And most of these things happen because you've got very sharp features. Like here, you've got a very sharp corner. You've got a tooth going into the other. And these corners are being sharp, you really create a localized plasticity, and damage is very, very local. It only happens really very close to these corners. So one of the ideas was, let's try to understand this from a mathematical point of view. Can we actually try to study problems in which you have these important features happening, for example, when you contact between spline shaft there, and try to understand if we can predict damage looking specifically at those features. So, and in fact, that links very well with what people do in fracture usually, which is just looking at, for example, if you have a notched component, you're really looking at how critical load makes crack start from sharp features. So this is a direct link with what you do conventionally in fracture, which says in fracture you want to find what the critical load is to get a crack going from a notch component or a cracked component, and why you get different kind of failures in different conditions. So what really I was interested in is understanding how brittle failure starts in some components, and that links, as I said, with what I've done before. But also I was interested in fatigue, because most of the failures we saw in the engines when we were actually working on these things were cyclic. So you actually need to go on for millions of cycles before you start seeing failures. So my research was actually really to understand both type of things, brittle fracture when you have it from notch samples, but also trying to predict cyclic fatigue in some of these components. And it turns out that actually you can use this methods in different ways to study these two problems. So back to this engine, let's go back to explain exactly what happens. So here you have your blade, as I said, is mounted on the disk. And you can have also lots of little blades mounted on the turbine side here, which are much smaller. This is a much smaller blade, but you've got the same problem. They are mounted with a dovetail joint onto the disk. So here, you want to know what happens in the contact between the blade and the disk as the engine runs. And in fact, the blade looks a bit like this. A fan blade looks a bit like that. It's a twirled blade. And in 3D looks like this. In 2D, if you take a slice, looks a bit like this. So you have a dovetail, and the dovetail is mounted on the disk. And therefore, if you think about after you run it, you apply the load, the blade vibrates, the blade has got centrifugal force. After a while, you might get cracks, and the crack usually starts at the contact between the disk, which is this one, and the blade, which is this one. Now, if that happens, unfortunately for us, this is the kind of damage you get. Your blade gets released, destroys half of the engine, and that is a 12 million pounds problem if you're lucky that you can land after that happens. And I think most of the time, this problem is contained. Even if it happens, you're safe. That's why flying is one of the safest things you can do in terms of transport. But still, you don't want this to happen. So, and the idea is all about this. So there is something in contact here, and you rub until there is a crack starting, and then the crack goes, fails. So here is really where I started, as was my PhD task. Said, can you try to explain this? Right. So the fact is, you don't want to do a test every time you want to know if something fails or doesn't on an engine. In fact, one of the biggest problems is that you can only do, you will really ideally will want to do only one of those tests that I showed you before, because that gives you accreditation for flying, and hopefully that is the only test you do, because that will cost you £8 million just to do the test. So everything you do at engineering level to design things properly needs to do with predicting things, predicting things in a way that you know that what you're designing wouldn't fail. Now, to do that, obviously, you can't go with testing real things, but you still need to test. And what you really want to do, you want to test something which is simpler, so you want to come up with tests that are similar to the real application, but maybe don't have the full 3D features. And in fact, that's what people at Oxford do in the Rolls-Royce Center. They take a system which has got a bladed disc here, which is just a coupon. And this coupon has a dovetail, which is these inside there. And what you can do, you can apply the load, so you can pull, you can take the specimen and pull it this way. You can pull the disc as well to replicate the centrifugal load that you have during flight. And then there are two shakers here, one there and one there, that can also show the oscillation on the blades as you fly. And when you go to the test and do the test there, you can actually just try to replicate the cracks and failures that you have in those systems. Cheaper, much cheaper, you can do more tests. Still not very easy. I mean, you can probably do, I don't know, 10 tests a month. If you want to change the coating on the blades, if you want to change the material of the blades, it's still a very long process. It still, takes a long time. Yeah, it's simpler, you don't test an engine, but you still, fairly, it's a non-straightforward test to do. And therefore, you can do something even simpler, and you can actually go one level down and say, okay, well, if I'm really interested in just what happens at the rubbing interfaces, can I not just take two pieces here that represent my blade and this blue thing that represents my disk, and just apply the load and rub them. And see and pull them in a way that I replicate more or less the state of stress that causes cracks there. And I do it on a simpler rig. This is just an inline rig, so there are two actuators in line with each other. One applies the load to the pads, to this orange-looking thing to make them go up and down. One applies this load to the blue specimen there, and that's all you need to do, really, until you get a crack. Again, it's simple. It's simple, much simpler. You can do a few tests, one a day, let's say. Very simple to mount. All you need to do have very simple specimens, and therefore you don't even have the complication of the geometry. And the fact is, yes, you can make it simpler. But how do we know that this test replicates the feature of this test, and this test in itself replicates what happens in a real 3D blade? And that is actually some of the reason why we got thinking about asymptotics, and that will become clearer later. But the idea is, yes, you can do all these tests. You can do it in different level of resolution, different scales. We need to do them so that the 3D view, the real component, can be replaced first by a 2D slice of your component, and maybe later by a simple 1D representation in line of your system. You can imagine 8 million, very expensive, once a year, to a couple of 2-3 of these per month. You can do as many as you like, because here you just have a straight sample and 2 pads to be machined, different materials. So there is quite a lot of attractive features into trying to scale down your test. And that's where my contribution came in to start. So I said, okay, let's say I have a blade and I have a disk, and I want to replicate how the crack starts in that disk. So, and I know, you start looking at words in here that appear with definition. So this is an incomplete contact, and I'll explain to you what it means properly later. But the idea is that I know that cracks will start there for various reasons. And I know that if I want to do a test with the other configuration, the one which is inline, the very simple one, I can have my little pad here being something which is basically a flat punch with the radius here. It's called flat and rounded. And here is my flat sample. So if you go back one slide, you're saying, okay, how do we know? So this is one configuration. You have one flat pad with some radii here, and a very simple flat specimen. And this is the other configuration. And the configuration has got all the geometry of a real blade, more or less, and so on and so forth. And I say, okay, so how do I know? How do I know when this is the same as that? And the fact is, if you actually look very close, and you look very close to where the crack starts, well, fortunately for us, the two of them look very similar. So all you need to do is make sure that that similarity comes into the maths. And that's what the asymptotic method will do for us later. Now, it turns out that it's not just that configuration that is very similar to what happens in that corner, but also a tilted configuration, or even just simple rounded sample indenting a flat, have got very similar feature to all of those. So it turns out that down to a certain magnification, imagine you're zooming in, imagine you just have a microscope and you just zoom there in that corner. Now, to a certain level of magnification, it turns out that that problem is very similar to that problem, but also to that problem or that problem. So it turns out that mathematically you can reconstruct these problems and actually find a way to apply the loads in each of them so that what happens near this corner is the same for all of them. And only if you do that, then you'll be sure that if you do a test with this, with some specific loads applying, then you're replicating what happens in the real larger scale test. So that was the idea of part of my PhD there, saying, can we just develop something that allows us to scale or change specimen or configuration, but keep the nature of what happens in the corner where we know the crack starts. Right, how do we do that? So to start with, again, this is one example. The other example is, I was mentioning before, spline shaft. Yes?
Methods doesn't apply.
You will see it later, but in reality, it's all about modulating these loads and these loads, or these loads, so that you can replicate the state of stress there. The idea is that you need to come up with a way to modify, say, these loads to obtain the same state of stress that you get from the load on the blade when it runs in an engine. The idea is that you will need to scale those so that the state of stress there is the same as state of stress there. And that's how well you do. The asymptotic solution allows you to do that because you have only two parameters to change. And that scaling is easy to do. If you had to do a scaling based on the full state of stress, you'll be scratching your head for a while. Okay. Good, interrupt me whenever you like. That's what I like. Now, as I said, this is the other example. You've got a spline shaft. So in this case, as I said, I've got a male and a female shaft coming in, and they turn and they transmit torque. And they transmit torque by having contact between the teeth and those points. And as you can see here, there's a sharp corner there, sharp corner there. Yes, they got some tiny radii, but actually they're very sharp features. And the idea is these things crack, and these things actually have proper failures sometimes. These are can be as dramatic as the fan releases you've seen. And these are not just in air engines. You'll find there will be lots of couplings in different transmission systems. And the idea is, okay, so we need to understand those as well. And those are slightly different from the previous one. So the previous one, let me go back for a second. The previous one has got one feature in common. And as I said before, they're called incomplete contacts. Why? Because when you merge one body into the other, the transition appears here to be smooth, and therefore there is always a radius of curvature between the two parts in that. That's what I call incomplete. I mean, the real definition will come later, as I said, but they're incomplete because the pressure between the two bodies in contact goes to zero at the edge. That's really what happens. Because you've got this radius, the pressure at the edge is zero. Whilst in these, they're called complete contacts. That doesn't happen. In fact, what happens there, if you look at individual teeth indenting with each other, these teeth, because they got sharp features here, say you're now zooming into one of these corners, it looks a bit like this. It looks like a flat punch, sharp, indenting a surface. Now, those contacts do not have zero pressure in the corner. Because you've got a very sharp feature here, you end up having very high pressures there. You've got singular pressures there. And that's why there is an intrinsic difference between the two sets of contact properties. Okay? So I'm not going to go, just try to understand the fundamentals. I'm not going to pretend that in 3 hours I can explain everything to you. But try to understand the basic concept, because that's all you're going to get from this. So, now we've defined the two sets of contact problems we want to solve. And obviously we want to find a link just like before. Remember what I said before? We want to go from the plate onto a simple test, which is flat and rounded. And here we want to do the same. Why can't we go from testing one of these to testing something we just got, just a square punch over a sample and slide it and try to break it? Can we do that? And the idea is yes, we can do that as long as we can replicate the state of stress around this point with the state of stress around this point. And then our test becomes as simple as the other one. You can just have a flat punch with a specimen and rub them until the crack starts. So that's all the fundamental. This is actually what we're trying to do. Now it turns out, especially if you look at these sharp problems, and that's where I'm going to start from. It turns out that, so this is the test rig that I showed you before. So imagine this is one of the samples, this is one pad, this is your sample. You can actually have a sharp interface there. This is the spline shaft, and again, apart from the angle at which these contacts, you can have that described in this way. But also you have other configuration. You can think of lots of problems that have this kind of issue. So imagine you've got a cantilever beam and you clamp it, and you clamped it with something which is fairly sharp. If you try and apply load to the cantilever beam, you'll have that corner actually has got the same problems as that corner or that corner. So the idea is that you can represent a lot of things with the same solution of a simple problem that has got a sharp corner, as long as you know how to do it. And that's what I'm going to take you through now. I'm going to take you through how to reproduce the state of stress in any of these, try to make sure that they are similar to each other. Okay, so that as a complication. And the complication is that studying these type of problems, so here I'm just now going to focus on this problem where you have one body which has got some angle of indentation versus something which is flat. Okay? And if you wanted to apply, so most of the contact problems, if someone knows about contact, knows that if I have something and I press this body against something flat, one way to solve that problem is assuming that both bodies are semi-infinite in nature, because there are lots of solutions for those things. Now here you cannot use that, because here you've got a 90 degrees, for example, corner there. So that cannot be an infinite body. In fact, it's got lots of material missing. So, but what comes in our aid is the fact that, let's for a second assume that this is glued, completely welded to the bottom material. And let's for a time being assume that those two materials are the same. So this is material 1, this is material 2. Let's assume material 1 and material 2 are the same for the time being. And let's assume that this interface is completely glued. It's actually perfectly welded, the same material. So this problem, which is intrinsically a contact problem, becomes the same as a notch problem. All you're doing, you are rotating this, and a notch problem, you usually start with a problem like this. Here, because we glued this interface, the two problems are identical. Now, we'll see later when we can assume that the interface is glued, but that means that if you want to solve a contact problem, which is a contact problem which is a punch indenting an alt plane, we can actually very easily think of these in the first approximation as a notch problem, where the notch has got the angle given by the interaction between the punch and the alt plane. So that means, and that's where the link with the fracture comes in, that means that if I want to study a contact problem, I could start by looking at notch specimens. So I can start looking at what happens in the corners of uniform materials with notches. So before we go back into contact, now I'm going to have a very large digression on notch samples, and now you study notch. And the whole idea is that we want to study what happens very close to these corners, or very close to these notches. Because, as I said before, if we know how to characterize what happens close to those notches, we might have a chance to characterize what happens close to those contact interfaces. Following? Good. If you go to sleep, don't worry, go to sleep, because it's Sunday morning, but give me a word of warning, and I might just excite you in some other way. Okay, so this is the background, this is really the motivation. Now we're going to go through the background, and we need to do a bit of maths. The maths is not very complicated. if you stop at some point. I mean, it can get very complicated, but I'm not going to go very complicated. And I want you to grasp the concept. I want you to understand very simple maths, where very simple maths can take you, because you have already done this mental exercise of analogies between different problems. So, these you all know, right? And you've actually seen it yesterday, because I'm sure Sylvie has done a good job at telling you about fatigue and cracks and so on. Right, so if you have a crack, or if you have a notch in reality, you know, mode 1 loading is when you load the sample in a way that opens up the crack. And mode 2 is when you load the sample in a way that actually you're loading it parallel to the direction of the crack in a way, in plane, but inside. And mode 3 is when you're actually loading the crack to open it in the third dimension. So you're trying to open the crack in a way which is orthogonal to the crack line. Yeah. Now, this is a crack. You can do the same with a notch. So the idea is that we can always think of a crack and a notch being loaded in one of these modes. So you're fairly familiar with mode 1, mode 2, mode 3 crack loading. And we're going to try to use this to study our notch components. So, and here is where the maths comes in. How we do it like? Right, so here is our problem. I'm going to try to do this as quickly as I can, but not too quick. Here is your notch problem. So usually you define the solution of a notch problem looking at the bisector of the notch, and you identify your radial coordinate as being coordinated along the bisector, and the angular change of your stress field through the angle theta, which is taken 0 from the bisector, and then it goes all the way. Okay, so if you have a V notch like this, usually you have an angle that characterizes the notch. It could be either the angle from the notch face to the bisector, or any other angle that you think takes into account the angle of the notch. So to start with, let's imagine we take this notch and we apply load. We apply remote load, and it could be pulling it, stretching it, deforming in the third dimension, whatever. So here is our load. And the first thing we want to do, we assume that this is a planar problem for now, 2D. And we assume this is semi-infinite. So if I take any other dimension in the problem, it's so big that everything, so the notch is very small compared to the tip. It's far away from any other boundary. It's a semi-infinite problem. So in that case, you can apply Williams solution, which is itself an asymptotic technique, and assumes that the stress function that governs the solution of this problem is a very simple function, which is a power law in R and a trigonometric function of theta. And where does that come from? It comes from here. Obviously, to solve the problem in elasticity in solid mechanics, you usually start with a biharmonic equation, and then you say that biharmonic equation, in this case, is going to be an equation in R in theta, and phi is the potential function of the area stress function that you want to find that solves the problem. So if that is the way you write your biharmonic equation, you can actually define the stress field as a function of the derivative of those stress functions. So again, if you never come across this, all there is there to understand is that for the system to obey equilibrium and compatibility in some form, you need to satisfy this equation, and the equation can be satisfied for a certain function phi. That function is what you want to find to get your solution to your problem. And if you define phi, you can define all the stress field. because the components are a function of the derivatives of phi. So, because the problem is self-similar, so the problem is semi-infinite, and it's also symmetric with respect to the bisector. Whoever solved this first, that we can debate with who that is, finds out that actually one function that could satisfy the solution of that equation is a variable separable function of the kind we've seen before, r to the power lambda plus 1 multiplied by a function of theta, which is a trigonometric function of theta. Okay, so Williams plugged everything in there and say, okay, if that is the biharmonic equation, and I assume my function has got that form, what I'm solving here becomes this. Right, and for lambda different from plus or minus 1, the solution becomes this. So you have phi can be expressed as r to the power of lambda plus 1 multiplied by this trigonometric function of 4 coefficients a1, a2, a3, a4. I'm not going to go into the maths very much, but I just want to show you where it comes from. That means that if you substitute in the equation of stresses and you compute the derivatives, the three stress components in 2D comes up to be lambda to the multiplied by r to lambda minus 1 multiplied by these three functions that identify sigma rr, sigma r theta, and sigma theta theta, which are the three components of stress in the Cartesian axis. Now, this is what we have, and then you need to do a few manipulations. So the first thing you need to do is apply the boundary condition to find some of these constants. And what do we know? We know, as a boundary condition, what do we know? We know along this, the stress orthogonal to this must be 0, and the shear must be 0. This is a free surface. You cannot have any stress, either orthogonally or tangentially to that. So therefore, you apply that and say sigma theta theta and sigma r theta must be equal to 0 for theta equal plus or minus alpha. With plus or minus alpha, identify our edges. That allows you to solve a set of 4 simultaneous homogeneous equations in A1, A2, A3, A4. More synthetically, really just solving 2 sets of equations, one for the symmetric part of the system, one for the antisymmetric part of the system. Really, these can be split into symmetric and antisymmetric solutions. You end up with these 4 equations really can be written this way. And if you look at that, it's a classical eigenvalue equation, and the roots can be found by solving. So if you take the symmetric part, and you need to find the roots of these problems to find lambda that satisfies the symmetric solution, and the roots of these problems for the antisymmetric solution. Now from now on, I'm going to call the symmetric with 1 and the antisymmetric with 2, because one corresponds to the mode 1 symmetric loading and the other one corresponds to the mode 2 antisymmetric loading. Okay. So when you solve these two equations, really, you end up, by solving the top one, you end up with a characteristic exponent of the area stress function that solves the problem in mode 1. So what you're getting that for different values of alpha, here, so I'm going from 180 to 360 because 180 corresponds to, if you go back here, alpha 180 corresponds to being a track, and alpha, alpha 180 corresponds to, actually I think alpha is defined in slightly different ways here. Oh, 2 alpha, sorry. Okay. So 2 alpha. So 2 alpha is defined such that if you've got alpha equal 90 degrees, you have a flat sample, there's no notch. And if alpha is equal 180 to 12 is 360, you've got a track. So you go all the way from a flat to a track. And here is what lambda 1 does. Lambda 1, and I'm plotting lambda 1 minus 1 because it's convenient, goes from minus 0.5 to 0. And if corresponds to the well-known solution for a crack, where you have a square root of r as being your solution, and that corresponds to a zero value, which corresponds to not having any singularity for a flat sample. Now, the intrinsic nature of this problem tells you another thing. It tells you that anywhere you are, if lambda 1 minus 1 is always negative, you always have a singular solution. So the solution is singular in nature. Now, obviously, the only time when it's not singular is when that notch becomes so big that you have a flat sample. So in mode 1, no matter what you're doing, even if your singularity becomes weaker and weaker, so if you go from a crack to a larger notch, yeah, it's still what the stress field in the corner, due to the application of a symmetric load, it's singular. There's nothing you can do about it. Now for mode 2, so when you solve the other equation, you get mode 2, and then therefore you get the exponent of your power law function, r to the lambda 2 minus 1. The lambda 2 minus 1 exponent is singular, the same singularity as we know for a crack, but then it's weaker, it's not as singular as the other one. Up to a point, this angle is about 254 degrees. Beyond which, so if you keep expanding the notch, the solution is not singular anymore. So your solution is not singular anymore. Your stress field becomes what we call it bounded. So your solution goes from a certain form to a completely different form. And what it means is that the solution, definitely from that point onwards, is always dominated by mode 1. What I'm trying to explain mathematically is that if you actually go back to here, if you have a crack, so if you make this notch angle very small, the two solutions, if you look at loading the crack this way and loading the crack in mode 2, if you have a crack, mode 1 and mode 2 give you a singular solution, and the magnitude of the singularity is the same. The moment you expand the notch and you make the notch wider and wider, that is not the case. So the singularity due to the mode 1 loading is much higher than the singularity given by the mode 2 loading. So what I'm actually saying is, when there is a notch, you shouldn't be thinking always that the singularity of the two modes of the solution is the same. You should always think that the singularity of mode 2 is always weaker than the singularity of mode 1. So mode 1 is bound to dominate the solution. Yes?
So, if I understood well, there's a certain angle beyond which there's a sharp transition from a singularity to a additional boundedness.
So what you're getting here, so if you set yourself to, let's go back to the picture, because I think that's better. So set yourself to start from a crack. So let's make this angle very small. You set yourself starting for a crack, so alpha is 180, 2 alpha is 360. You know that the stress field around the crack tip, that's something that you've seen also yesterday, you know from before, is characterized by a stress field which is 1 over square root of r. Okay? And that is valid for mode 1 and mode 2. The singularities are exactly the same for both modes of loading. Okay? And that corresponds to me telling you, if you solve William's solution, you are here. Yeah? Now, the moment you start opening, as soon as you open the notch becomes 10 degrees wide. So the notch becomes 10 degrees wide, you are about the 340, you're here. The singularity in mode 1 is almost still 1 over square root of r. Now, in mode 2, it's not. In mode 2 is not 1 over square root of r, it's 1 over r to the power of 1.41.
But let us assume that the sharp notch that is working on under mode 2.
Yes.
That means that we have an angle beyond which we have a abrupt change.
I was going to get there.
From infinity to 0.
Yes.
Of the stress.
So what happens there? So I now keep going. opening, opening, opening. Now I open, and my angle, so 254 divided by 2 is what? 127 degrees. So I make this angle 127, which means my notch has become fairly big. At that very point, the solution tells you you're here. Your mode 1 has got a singularity which is still 1 over r to the minus 0.42. That one has got 1 over r to the 2, right? Which means you've become bounded. So at that point, your solution for mode 2 is not singular anymore, it's bounded. And from that point onwards, it will always be. So all of this region of notch angles have a bounded solution. Yeah. For mode 2. Mode 1 is always singular. Yeah? And that's important because it allows you to, and then we're going to talk about this later, it allows you to understand that mode dominance, which mode dominates depending on the load for different notches. So the difference is, for a crack, you always know both mode 1 and mode 2 have got the same strength. Now for a notch, that will not be the case. And because that is not the case, the treatment you have of a notch must be different from the treatment you have of a crack. And that's what we're going to do later. So this is really fundamental solutions. And that is exactly what we were saying. In the next slide says this. If you have, sorry, 257.4 is the angle, but basically obviously both Eigen solutions are bounded if you have a flat sample or a re-entered notch. So anything below 180 really is not singular. Anything that is between 180 and 257.4 is singular in mode 1, bounded in mode 2. Everything that is beyond it is singular for both. Now, so this is really a good plot to show what we have. So this is the solution to the very simple, the simplest Williams problem. What you can do then, if you have found your lambdas, then you can actually, because now you've got your eigenvalues, you can go back and find your eigenvectors. You can actually go back and solve the full problem. So now you know that for a certain alpha, you have a certain lambda. So you can go back in the symmetric part of the solution, for example, you substitute lambda 1 to your lambda, and all that is left is A1 and A3. Yeah? Now, it turns out, for a given angle, this ratio is fixed. A1 over A3 is a fixed ratio, and that actually becomes the factor that you need to put in front of your equation to find the stresses. So really, the ratio between A1 and A3, you can actually imagine you just divide everything by A3, you get A1 over A3 in all of these equations. That factor can be taken out of the equation and becomes your stress intensity. That's how you get the first equation that is written as Kr something to the power of something multiplied by a function. So as we said at the beginning, we're going to end up at any state of stress for any angle of notch, say for mode 1 loading, will be written as a generalized stress intensity factor K1 multiplied by r to the power of some number. This number will be read from the graph I showed you before, is the lambda 1 minus 1, multiplied by a series of trigonometric functions which depend on the angle of opening. Okay. So for each of these, so for example, alpha equal 150 degrees 0.5, I don't know why I picked that number, but that's right. Lambda 1 is 0.512, you just plug everything in, you get the full solution. That's how really you derive a solution for a notch stress field in mode 1. Now mode 2 is the same, you're going to get, instead of K1, you're going to get K2, which is A2 over A4 in the equations from Williams, and you get another trigonometric function with another exponent there. But basically, you can have any combination of stresses there for a given remote applied load. And obviously, K1 and K2 will depend on the remote load, and we're going to go back to how to compute those later. So, therefore, what I can do here, I can write stresses in this form. I can write any component of stress as a term given by mode 1, k1 r to the lambda 1 minus 1 by a function of theta, I call it 1, plus the mode 2 term, which is k2 r to the lambda 2 minus 1 by a function of theta, f2, plus other terms. Now all the terms they add to that are bounded. So it's like we're taking a series representation of the stress and we're saying these two are the dominant terms, well, especially in some regions for a certain alpha. Now, obviously, that is not the full solution. If you keep looking outwards, you're going to let other terms come in to describe the full stress field. So this is really a very good description of the stress field, very close to the tip. There will be other terms, but we're not considering them yet. Okay? And these terms become more and more important as the other dimension around the notch flows into the notch. So if you have a notch which is very big compared to other dimensions, the bounded terms might become very important because actually they are felt by the notch very soon. So, series expansion solution, we just talked the first two terms. They're singular up to a point. One of them we know can be bounded, but we can neglect all the other bounded terms for the time being. And it's really a solution which is very similar to a track solution. The only thing that changes is that these exponents and these factors change with that. Now, one thing we can do is for each of these stress fields, you know when you got a stress field, you can define the invariants. So the one thing that you can define is the second invariant, or the deviatoric invariant of stress, which in polar coordinates is just sigma r squared plus sigma theta squared plus blah blah blah. And the idea is that if you have that, you can start plotting and looking at what this invariant looks like. And actually, in elasticity, you can also say that when the invariant becomes gets close to the yield, what the invariant due to the yield stress, then you actually have plasticity. So you can actually do all the calculations you do with the track, saying that the plastic radius can be computed through this. So one of the things you can do is to look at some of them. So I'm going to go through a few of them, and I'm going to show you what the nature of the solution is. So let's take a 2 alpha equal 300 degrees. That literally means we've got a notch of 60 degrees in there. The component of stress look like this. So this is sigma theta theta. I'm applying on mode 1. So this is sigma theta in mode 1. This is sigma r theta in mode 1. And if my singularity of mode 1 is lambda 1 minus 1 is minus 0.488. And if I look at my second invariant of stress, which you can think almost as being your Mises stress in a way, your plots of those surfaces will look a bit like this. Okay? This is for mode 1. Now, if you look at the mode 2 solution of the same problem, this is what the state of stress for the mode 2 part of the solution looks like. This is in theta theta, this is in r theta, and your square root of J2 stress type will have a surface which looks like this. Obviously, the more you expand, you change k, the more that surface changes, but it's self-similar, so it changes in dimension. Right, so at 300 degrees, both of them are singular. Now, the singularity for mode 2 is lambda 2 minus 1 equal minus 0.274. Let's say we now take a notch, and this notch is very big. And it's 220, 12 is 220, so we are beyond the point where mode 2 has become bounded. Obviously, the symmetric solution will have a singularity lambda 1 minus 1 minus 0.303. The square root of J2 plot will look a bit like this. These are the stress components. The good thing about the thing that you need to remember here is that mode 2 solution, the anti-symmetric solution doesn't exist, it's bounded, so you cannot plot it in the same way. You can actually you don't have any singular field. It's a very simple bounded field. And if I do the last one, if I go down all the way to a track, alpha equals 360 degrees, you obtain what you already know, the perfect solution for a track, which is lambda 1 minus 1 is minus 0.5, and the J2, square root of J2 surface looking exactly like that. Those lobes are the typical lobes you see in a track solution, and the mode 2 solution having exactly the same singularity, showing a square root of J2 plot of this shape. Yeah? So, we now know that for any notch, we can find out if it's singular in both modes, if it's singular just in one mode and not in the other one. But certainly if we are loading it in plane, and we have both mode 1 and mode 2 loading, we certainly have the possibility to study this. Now, a little digression. So in terms of a summary, for mode 1 and mode 2 loading, we can look at the stress field around the notch tip, always as a combination of the two fields given by the solution for symmetric part, this there, and the anti-symmetric part, that there. And we now know that the solution of lambda 1 and lambda 2 come from those two little equations there, and the solutions are both singular in a range, and one is singular, one is bounded in the other range. Now we've done mode 1 and mode 2, and what about mode 3? Mode 3 is very simple, so I need to give this. Okay, so mode 3, it's fairly simple. You're taking your crack and you're trying to twist it out of plane. So this is your crack, my fingers are the crack. All I'm doing, I'm pushing it so that it opens out of plane. Now in elasticity, this is an uncoupled problem. What you're doing out of plane is not coupled with what happens in plane. So the solution to the problem is actually simpler than the solutions to the mode 1 and mode 2 problem. And again, I'm not going to go very much into the maths, I'm going to just show it on the board. But you're solving a very similar problem. You have a equation which is similar to the biharmonic equation, although it's not biharmonic there, it's actually simpler. And then you actually then you can write the shear stress in the out of plane direction, the Thor RZ, as a derivative of the function that satisfies the You do exactly the same procedure. You say exactly the same as before. The solution of that equation is coming from a potential function which is not like phi that we had before, but it's very similar to phi in the sense that it's variable separable. Again, you can imagine a term which is r to the power of lambda, where lambda is the eigen value of the solution of the problem, and another equation, another term there. And that is a function of the angle. Now t, we're imagining t is the angle of rotation out of plane. Again, to cut a very long story short, you assume that is the solution, you plug back into that equation, you then obtain a solution for that, which is r to the lambda multiplied by a trigonometric function with two coefficients, C1 and C2. You apply the boundary, well, the only two non-zero stresses are toward z and toward z theta. So you can imagine that when you're opening a crack, just this way, you have only two components which are non-zero stresses. And these are the two components, the toward z and toward z theta. They're both, one is in plane but going downwards, one is out of plane. And the solution to this problem comes down to finding the eigenvalue again. The eigenvalue comes from this very simple equation. And therefore, lambda is pi over 2 alpha minus 1. And therefore, if you plot lambda 3, so the third mode lambda, as a function of alpha like we did before, now mode 3 comes to be singular, always singular, unless you get the reentrant notch or a flat sample, just like mode 1. But the nature of the singularity is such that it's always weaker than mode 1, apart from when you are on the track or in a perfectly flat sample. That's where the two singularities merge back into each other. This obviously is a real singularity. That is actually is a real analogy. That's in that case you can't really deform in mode 3 a flat sample. So that is really a mathematical feature, but you can't really you don't get much out of that. So the idea is though that now we've done all three modes, and for them we know that we can write the stress field if we apply mode 1, mode 2, and mode 3 loading as a sequence of three terms. There's going to be the mode 1, K1 term, plus the K2 term. And if you have mode 3 load, you're just going to add the third term, which again is an expression very similar. You can actually add a K3 term, r to the power of lambda minus 1, where lambda comes from this equation, and so on and so forth. But basically, because the solutions are uncoupled, the mode 3 can be summed up directly onto mode 1 and mode 2 in this type of solution. Now, to summarize the entire Williams solution once and for all, now we know we have three modes. Mode 1 is the strongest, always singular, unless you go the re-entrant notch. So any alpha between 90 and 180 degrees will give you a singular solution, and is the strongest solution. And mode 3 is an intermediate strength, is always singular, but it's weaker than mode 1, in case you have mode 3 loading. Now mode 2 is always the weakest. In fact, it's bounded for 2 alpha less than 257.4 degrees. And obviously when you go to a track, all three of them are exactly the same, and they go to 1 over square root of r fields, which are typical of a track in all three modes. So really the track is the generic problem of a notch, where all three modes have the same solution in terms of eigenvalues, and they all go to the same stress field. Questions? No? All okay mathematically so far? I mean, it's fairly straightforward. I just wanted to make sure that you know why we're talking about all of this, because later it will become important. Right, let me see. Let's do another 10 minutes and then we stop, shall we? Okay, so in the next 10 minutes I'm going to give you the background on how to take this mathematical background and apply and try to make sense out of stress fields and therefore propensity to failure in fracture, in fatigue, due to the stress field development in notch. So to do this, I think I'm going to do a slight change in nomenclature, because that is going to help us understanding a few things about notches that are very difficult to extract from notches otherwise. So the first thing I'm going to do is this. So I'll just look at mode 1 and mode 2. Forget about mode 3 for the time being. It just complicates things unnecessarily. The first thing I do, I take my standard formulation and I rearrange things. Well, that is really something I did on the back of the envelope with David Hills when we were having a coffee, and say, okay, so what do we do here? So we want to come up with something that has got an intrinsic length scale into the formulation. So what we really wanted to do is to come up with a rearrangement of the equation so that we had an intrinsic length scale coming out of the problem. And also we had something that which controlled the strength of the applied load. So what we did, we defined these two quantities. D0, which is really turns out to be a very simple ratio of the mode 2 stress intensity divided by mode 1 stress intensity to the 1 minus lambda 1 minus lambda 2. And G naught, which is again a combination of K1 and K2 multiplied to some power of the eigenvalues that correspond to the solutions. Now, it turns out that these, as we arranged it, as the unit of length. And it turns out that these so unit of stress. And therefore, you can rearrange the Williams equation into this. So stress at any point in the three components in plane divided by G naught is equal to R divided by D naught to the lambda 1 minus 1 multiplied by the usual F1 in theta plus the second term exactly the same. So because this is just a function of the ratio K2 to K1, it turns out that actually identifies the boundary between when the solution is mode 1 dominated and when the solution is mode 2 dominated. Now the reason why this is a big issue is because imagine you're setting a fracture test. And imagine you're setting a fracture test where you actually try to define the angle of your notch and the load, the remote load, so that you have only mode 1 or only mode 2 failure. Lots of people say, I want to do a test in mode 1 and I want to do a test in pure mode 2. Well, it turns out that that is not as simple as just applying the load in a certain direction. You can't do that. You need to actually look at what the real state of stress is there and then try to understand mode dominance, which mode dominates. And the only way to look at the mode dominance is to look at the stresses, not at the load. You need to look at the stresses, and what stress is dominating the solution is what your mode dominant. And I think that's what we try to do. We try to actually go and understand much deeper how we get mode dominance. And this allows you to do so, because I think this redefinition of Williams' solution brings out the length scale, D naught, which will tell you actually almost automatically if you are in mode 1 or mode 2, up to 1. So, and that's how we do. That's what we look at next. We look at mode mixity. So we want to quantify the mode mixity of the process zone. So we want to look at what is the area around the notch which is important. So where things happen. For example, if a fracture starts, where is that the process zone, the region over which you exceed a certain stress happens. We want to estimate the shape of the process zone depending on the angle of the notch. But we also want to see how, and we do that based on simple violation of von Mises criterion. But also we want to look at when we are in pure mode 1 and pure mode 2. Because I think, as I said before, one of the big issues is if I apply a load to a certain specimen, how do I know if I'm in mode 1, mode 2, or mixed? And that's how we did. So, again, it turns out, and I'm going to stop after this because it'll take 10 minutes to get the next bit. It turns out that you can almost think of D naught, this number here, defined as the ratio between K2 and K1 to the power 1 divided by lambda 1 minus lambda 2, as the region over which K1 dominates. And beyond that, you have a region in which K2 dominates. And I think that will become clearer when I show you some plots in the next few slides. Questions? Should we stop here? Have something to drink? Yeah? Or do you want to continue? I'm so eager to know that we should continue. Right, let's stop. I need something to drink.